Okay, so we started yesterday looking at the R ratio. And I said the reason to do it is that it's one of those simple examples we can use to see how infrared singularities appear and how eventually we cancel them. Physical observables do not have any singularities left at the end of the day when they are infrared safe. So today we will move, we did the leading order calculation yesterday, we will move today towards the next leading order calculation. Okay, so we'll have to start above, to stay above the line, okay. Okay, so our process was the following. And we'll be emitting a gluon now. So this is my P1, this is my P2, this is my anti-quark, and this is my quark. And so the emission can be of two legs. So we have two diagrams to consider in this case. Here's my gluon again. And remember, we are focusing on this part here. Because the production part cancels when we take the ratio to the muon plus muon minus. Okay? Okay, so let's start with the phase space. And I guess I have to move here. So yesterday I wrote the flux factor as 1 over 2 times square root of s. It's actually, that was a typo. That's 1 over 2s, okay? But it doesn't affect the R ratio because when you take the ratio of the numerator to the denominator, it cancels. So the R ratio is the same. So we have 1 over 2s, which is the flux factor. And then we integrate over our final state, ddp1 over 2 pi to the power d times the on-shell delta for each of these final states. And we do the same with the gluon. And then we have the conservation delta, which says that P1 plus P2 plus Pg is the same as the off-shell photon momentum. Okay, so what I will do right now is remove the integral over the Pg using this delta function. And that gives me 1 over 2s. And there are other factors. I combine the factors with 2 pi's together, so I have 2 pi to the power 2d minus 3 ddp1 ddp2, and now I have removed the Pg integral. And therefore I have delta of P gamma star minus P1 minus P2 squared. And so I will be working in the center of mass energy, and I will define the components of my momenta as follows. So P gamma star is square root of s times 1, 0, 0. P1 is just E1 times this, and P2 has a polar angle in it, so we have E2 times 1 as theta, which refers to sine theta, 0, and cosine theta. So this is cosine theta. This is sine theta. And it's just... Okay, so I just wrote the phase space integral. I removed the gluon integral by using one of the delta functions, the conservation delta. And so I'm left with this term in here. And now I just wrote explicitly the parameterization of my momenta in the center of mass frame. And this is what they are. And I'm using a shorthand notation, S theta and C theta, to refer to the sine theta and cosine theta. So just to have some kind of small notation so we don't take a lot of space in here. All right. So now you can write explicitly all these integrals in terms of the energies and the angles. And so this is 1/2s again. Now I have integrals of my energy. These are my angular integrals, the omega 1, the omega 2. And then the conservation delta now becomes, or not the conservation, this square here becomes the following. Okay, so far so good. Now the omega 2, because we have this integration over cosine theta, so the omega 2 splits into a d minus 2 angle omega times dc theta times s theta to the power minus 2 epsilon. And now, because there is no dependence on this azimuthal angle omega d minus 2, I can integrate inclusively over it. So I can integrate over it, and I only keep explicitly the c theta integral. So let's write it explicitly here. Okay. So now we got explicitly all my terms. We've got omega d minus 1, omega d minus 2, we have an integral over E1 and E2. And I have my angular dependence, sine theta to the power minus 2 epsilon, d cosine theta, times the delta function. Okay. So far, so good. It's just plugging in the definitions of the phase space integral, the momenta, and that's it. I haven't done anything yet at this point. So now remember that our goal is to study the infrared structure later on. So I'm going to introduce some variables that simplify this study later. And so I'm going to introduce variables x1 and x2, which are related to the energy. So x1 is 2e1 over square root of s. x2 let me write it here. So when you move from the integral over the energy to the integral over axis, there is a Jacobian that you have to take into account. So now dE1 is square root of s over 2 dx1, and the same for dE2. All right, so now I go back and plug them into my phase space integral. Now we have the dependence on x1 and x2 explicitly in my integral. So we have x1 over x2 divided by 4 to the power d minus 3. And I have an angular integral d cosine theta times 1 over 1 minus cosine theta squared to the power epsilon. So this 1 minus c theta squared comes from here. Okay? I just wrote this one now, sine theta to the power minus 2 epsilon as 1 over 1 minus c theta squared to the power epsilon. Okay? Yeah?
What's the epsilon?
So we are working in the dimensions. So dimensional regularization, we are going to regulate all singularities with dimensional regularization, which means d equals 4 minus 2 epsilon. Thank you. And no, they are still there. I mean, yeah, there's still an integration over x1 and x2. Okay, so, and I believe there is one more term that I'm missing here. That is the delta term. The delta of s minus s times x1 plus x2. Let me get it right here. Minus s plus s over 2. x1, x2 times 1 minus c theta. And then there's a parenthesis here. Okay, so now I will use this delta function to get the value of c theta in terms of x1 and x2. Okay? Can I remove the stuff on this blackboard? And so we use the delta function to get the value of So when you do that, what you find is the following. The cosine theta is now 1 plus 2 over x1, x2 times 1 minus x1 minus x2. And the Jacobian is 2 over x1, x2s. Okay? And so if you want to get 1 minus c theta squared, which is what appears in our denominator in terms of x1 minus x2, x1 and x2, you get it from here. So you will get 1 minus c theta squared is 4 times 1 minus x1, 1 minus x2, minus 1 plus x1 plus x2 divided by x1 squared, x2 squared. And now I will introduce a new label, x3, which is connected to x1 and x2. You will see why we are doing all of this later. So the minus 1 plus x1 plus x2, when I use this definition of x3, becomes just 1 minus x3. Okay? So now my phase space integral And so you see that it simplifies now. When you use these variables x1, x2, x3, you can write it in a much simpler way than what we had originally. And now I will do a next step and try to write this phase space for the reirradiation in terms of my leading order phase space. Okay, so remember from yesterday in D dimensions, our PS0, let me denote it as leading order. We found it is equal to 1 over 16s times 1 over 2 pi to the power 2 minus 2 epsilon omega d minus 1 over 2 to the power minus 2 epsilon times s to the power minus epsilon. So if I use this now and rewrite this line here in terms of PS0, I will get something simple. My phase space now PS at NLO is equal to this leading order phase space times these order factors. And that's it. So this is the expression of our NLO phase space integral.
But the x's you just introduced to simplify the expression, right?
Yeah, they are just, it's notational simplification, and also later you will see what end limits they correspond to when we look at the singularities. It's much simpler to work with the x's than keeping everything explicit with energies and angles. Okay, so this is our expression for the reading order, for the next reading order phase space. Now we move into getting the matrix elements squared. Which one should I delete? Okay, so real emission matrix elements now. Do you still remember the diagrams I drew at first, or shall I draw them again? You remember them, okay, good. So I will write the amplitude. We have two diagrams, so we have the sum of two terms. IM1 is going to be U bar of P1 So this is my first term plus the second term. Okay, so we have two terms to take care of. And I will refer to the first one by I1. And this second one is I2. So IM1 is simply the sum of I1 plus I2. And then remember, to get the amplitude squared, we are going to sum over final state spin and color, average over initial state spin and color, which is in this case, it's just a photon. It doesn't have a color. It does have polarizations. It's off shell, so we have a factor of 1/3. We've seen this yesterday already. Okay? So eventually you put these factors in there. And when you sum over the final state color, you have NC. All right? So let me start with I1. So it has the charge of the color, EQ, TS, U bar 1, and you can simply write it in a simpler form as minus EQ strong coupling constant over S1G So far, so good? So P1 plus PG squared is replaced by S1G. Okay? P1 squared is 0, PG squared is 0. You have 2 times P1 at PG, and that's the invariant S1G. So that's what I did here. The rest is the same. Okay? I can define it here. S1G is just P1 plus PG squared. And so this is our expression for I1. Now we have to calculate I1 times I1 star for the square of the amplitude. So that's the square. I1, this is I1 times I1 star. And then we are going to use the usual spinor identities. UU bar equals P slash for a massless quark. BV bar equals also the P slash, the momentum corresponding to the V for a massless quark. And we will also replace the sum over the polarizations for the gluon and the photon. Okay? And we have a sum of polarizations for the gluons. Which is simply minus delta AB times G mu nu. So all these relations will be used, and we also have the sum over for the photon polarization. So we average over the initial state polarizations, that's 1/3, and we sum over all other polarizations. So we have epsilon gamma mu, epsilon star, nu gamma is just 1/3 times minus G mu nu plus P gamma mu, P gamma nu over S, where S is just the square of the momentum of the photon. If you wish, it's the mass of the off-shell photon. So we just have to plug in all these relations in here, and that's what will give us a trace. So I will delete this one here. I will work out the color algebra separately. Okay, so I will work it out here explicitly. As you know, if you take, so from this square, once you plug these relations in here, you will have a trace. Okay, so you will have part of that trace is a trace over the color matrices that appear in here. So the trace over the color matrices TA, TB that will appear in here times delta AB is simply 1/2 delta AB times delta AB. We talked about this yesterday. The trace of TA TB is 1/2 times delta AB. Yesterday we said it's TR, and TR is 1/2. Okay, so this is now 1/2 times delta AB from here times the other delta AB we have, and this is simply NC squared minus 1 over 2, which I will rewrite as NC squared minus 1 over 2 NC times NC. I haven't done anything here. I just multiplied and divided by NC, and this gives me CF times NC, where CF is this piece here. Okay, so we just plug now this color result in our trace, and therefore I get the averaged sum for I1 star is just EQ squared CF and C that I just calculated, the third from the average of the polarizations, and then we have the trace of P1 slash gamma mu P1 slash plus PG slash gamma nu P2 slash gamma rho gamma sigma. Okay, and then I have also the minus G mu nu from the gluon polarization sum, and I have the minus G u rho Okay, so now it's really just a matter of doing some algebra. So when you multiply this G mu nu with the content of this trace, mu will turn into a nu. So what you will have, so let me see how to simplify it. Now, before we do that first, before we multiply with g mu nu, let me simplify it. So I will start by simplifying this term here first. Okay? Remember, p slash gamma mu p slash, as we've seen it yesterday, is 2 minus d times p slash. You will start by simplifying this piece. Okay, so this is mu sigma, by the way, sorry. Okay, so we have mu sigma, nu rho, p nu, p rho. So let me give a name to this trace. So the trace I just highlighted, actually, which has a trace of p1 gamma mu, p1 slash plus pg slash gamma nu times this rest of the terms. I will multiply first with this g mu sigma, and what that does is it will turn the index sigma into a mu, okay? And then I use the trace to move that gamma mu to the beginning of my trace, all right? And then I use this relation. Did you get it? Then I don't have to do it explicitly. And there are actually further algebraic steps. There are like 3 steps that you have to do. I will give you the result of those 3 steps. If you do not manage to get from this point here to what I will give you, let me know. Okay, I have it here scribbled on a piece of paper. We can go through it. All right? But you will need to use this relation. And another relation you will need to use is the fact that p1 slash pg slash is equal to 2 p1 dot pg minus pg slash p1 slash. So you will be every time using the property of the trace, the fact that you can rotate some of the matrices to the front. That would allow you to use identities like this. When you replace some of the product of momenta slashes with this, that leads sometimes into squares that vanish, so you lose some terms, and therefore things simplify. So I'll give you the result. If you don't get it, if you work it on and you don't get it, let me know, okay? I can show it to you separately. So what I get is d minus 2 aq squared gs squared and we still have the second tensor here, g nu rho. So in this first step, I just used this first g mu nu. In this next step, we will use this second bracket and see what we get out of the multiplication with the trace. So let me call the first term 1, and this is term 2. And I calculate them here. Term 1 is just minus the trace of PG slash gamma nu P2 slash gamma nu. And by now you know what to do with this term here. So this becomes D minus 2 times the trace of PG slash times P2 slash, and this is simply D minus 2 times 4 P2 dot PG. Now recall that SPG, S2G, sorry, is 2 times P2 dot PG, so I can just rewrite this as 2 times D minus 2 S2G. So that was the first term. Second term coming from the multiplication with this product of the momenta of the photon. We give the following. So we have 1 over S times the trace PZ slash P gamma slash P2 slash P gamma slash, and here we are going to use the fact that P gamma is just the sum of P1 mu plus P2 mu plus PG mu. Okay, so now if I take this and plug it in here for P gamma, you could see that the only term that's going to survive is the one coming from P1 mu, because P2 slash times P2 slash, that's 0, that's P2 squared, that's 0. PG slash times PG slash, that's PG squared, which is also 0. So at the end of the day, you only have contribution from P1. And so this term will just become term 2 becomes 1 over S times 2 P1 dot P2 times the trace of PG slash P1 slash, which is 2 S12 S1G over S. So now I have all the terms that I need for the I1 star piece. Okay? So at the end of the day, my I1 star is just D minus 2 So that's your final result for I1 star. All these calculation steps, you get something simple at the end of the day. Now, I2 times I2 star is related to I1 star by just interchanging 1 and 2, P1 and P2. So you can write it immediately. Let me just first write. So what is left now to calculate is the other term, I1 times I2 star, and I1 star times I2. These are calculation steps we have to go through before we can see really the singularities appearing in our matrix element. So bear with me. So next we need I1 star times I2. Okay, so I will write again explicitly I1 and I2 here. That's I1, I2 is EQ GS over S2G U bar 1 and now we take the product of I1 star times I2 And so by now you're familiar with what we should do. You have the spinor relations, you have to do the usual summing and averaging and so on, and that will give you this. We have a trace of P1 slash gamma mu And now what I did is I asked From to calculate this for me. Okay? So this is slightly more complicated than the other ones. I just asked From to do it. So we can be sure that what we are getting is really right. And so the result of that, I will show it to you. Are you all familiar with form? You know what it is? Okay. So this is 4 times minus 1 plus epsilon. I can write as 1 minus epsilon here. And so EQ squared times 1 over s, and then you have a long expression here, 2s s12 squared plus 2s s12 s1g plus 2s s12 s2g minus S12, S1g, S2g minus 2 epsilon S times S1g times S2g. And now this expression here between braces can be simplified if you know that. Let me give it a name. Or let me write it, 2s can I just this one here is equal to 2s times s12 times the sum s12 plus n s1g. And what is this thing here between square brackets? This is s. S12 plus s1g plus s2g, that's exactly your center of mass and energy squared, so this is exactly s, and therefore this is 2s squared times s12. So this long expression does get simplified a bit. I also want to write down the overall factor, which is four times 1 minus epsilon. I want to write it in terms of d, and so that is just 2 times d minus 2. Okay? And so we can write now the result for I1 star I2 plus I2 star I1, which is symmetric for I1 with respect to I1, I2. So you just interchange the labels 1 and 2. And so what I have it's just 2 times the average sum for I2 and 1 star, and so now we can write that, and that is the sum four times d minus 2 times EQ squared GS squared over S S1G S2G CF and C over 3 And so now you put everything together to get your amplitude squared. That's what we are going to do. And then I will express in terms of m0 squared.
I just have a small typo.
What?
In the middle line on the last one, it should be 2s1 to s1ds.
Which term are we talking about? Sorry?
Under the yellow bracket, the second term.
2s1 to s1 s1g. So s1, okay, yeah, there is a factor of s for sure, yes. Thank you. So once combining everything together, m1 squared now becomes, this is the average one. Now, as I said, I want to write m1 squared in terms of m0 squared. And just to remind you about m0, which we calculated yesterday. So m0 was m0 squared. We found it equal to 4/3 NC times 1 minus epsilon EQ squared S, and therefore my amplitude now squared becomes the following. All right, so this is our amplitude squared in terms of the invariance. And now I'm going to use the variables x1 and x2 I talked about before that I have introduced at the phase space integral. And the reason is that they make the infrared structure more transparent later when we start looking at the poles. Okay, so I will write just S1G explicitly and the rest should be clear. So S1G is 2P1.PG, which is 2P1. PG is P gamma minus P1 minus P2. P1 squared is 0, so I have just P1 dot P gamma and P1 dot P2. And then I have my momenta in terms of energies and angles, so I just have to write them explicitly now. So we have 2 square root of S E1 minus 2 E1 E2 times 1 minus cosine theta. And in terms of x1 and x2, this becomes x1s minus x1 x2s over 2 times 1 minus cosine theta. And just to remind you, let's put them explicitly in front of us. X1 was connected to the energy E1, so it was 2E1 over square root of S. X2 was 2E2 over square root of S. And C theta was 1 plus 2 over x1, x2 times 1 minus x1 minus x2. So I just use these relations to get S1G. And we are going to do the same thing with other invariants. And so we got S1G. We can simplify it after simplifications, which you can do in Mathematica if you wish. What we get is that S1G is simply S times 1 minus x2. Okay? It becomes pretty simple. S2G is just S times 1 minus x1. And so replacing the amplitude squared will give us something that is pretty short compared to what we had before. So we get m1 squared is simply 2CF strong coupling constant squared m0 squared over S times 1 minus epsilon x1 squared plus x2 squared plus 2 epsilon times 1 minus x3 over 1 minus x1 times 1 minus x2. And then we have minus 2 epsilon as well. And this is our amplitude squared. And just to remind you, x3 is connected to x1 and x2, so it is 2 minus x1 minus x2. Now, what do you see in the amplitude squared? Yes. Right, so you see that we do have singularities when x1 or x2 or both vanish. All right? x1 and x2 are related to S1G and S2G. Now, I will put all the relations one next to each other, so we do have S1G and S2G here. The only things I want to put here are E1, E2, E3, remember this is the energy of the gluon, This is the anti-quark. Energy. And this is the quark energy. So, when x1 equals 1, S2G vanishes. Okay? However, the energy does not vanish. So what kind of singularity do we have here? Collinear singularity. So x1 equals 1 implies S2G equals 0. And this is a collinear singularity when PG becomes collinear to P2. Similarly, you can see when x2 equals 1, S1G vanishes, but the energy does not vanish. Again, this is a pure collinear singularity, and it corresponds to the gluon being collinear to P1. What happens when both of them are equal to 1? When both of them are equal to 1, this one vanishes, and the energy of the gluon vanishes. And when that happens, it means you have a soft singularity and a collinear singularity. So we have a double pole in that case. So x1 alone equals 0, that's a single collinear singularity. So we have 1 over epsilon pole in dimensional regularization. x2 alone equals to 1 gives another collinear singularity. But when both equal to 1, we have a double pole, a soft and a collinear singularity. And those are sitting right there in our amplitude. Remember, we have so far calculated the radiation only. So x2 equals 1 implies S1G equals 0. That means PG is collinear to P1. Whereas x1 equals x2 equals 1 implies the energy of the gluon vanishes, and the gluon is half of the time collinear to P1 and half of the time collinear to P2. So soft double pole. Soft and collinear. So if I were to draw my space, my two-dimensional space for x1 and x2, this is 1, this is 1, this is soft singularity, this is PG collinear to P1. This is PG. So you can see the region of phase space you are integrating over. This is the allowed region. We're integrating over this entire region. This corner here has a soft and a collinear singularity. This entire edge has a collinear singularity when the gluon is collinear to P1. This entire edge of our phase space has a collinear singularity when the gluon is collinear to P2. So this entire area of my phase space has singularities that need to be taken care of. Okay.
I have one question regarding the structure of the amplitudes. This is like peculiar for Gaussian type processes that the reals factorize into a Born matrix element times factor.
This is actually not just the Drellian process. It actually appears in all sorts of higher order calculations. It appears, for example, in DIS. You will see things like that, Drellian. vector boson plus jet. So it appears in multiple processes, this kind of factorization. And you're right, it underlines all this higher order.
But in general, it's only in the soft and collinear limits where this happens, right? I mean, if I have a complicated process, it's not guaranteed that it will look like this over all the phase space.
If you have a complicated process, you will see, and you work in the soft or a collinear approximation, this factorization will happen. You will see it explicitly. And it is what underlines all these subtraction methods that people use to remove the singularities, whether it's at NLO, NNLO, and so on.
But in the hard part, there's only holds for Dralian-like processes, I think.
The hard part is finite. We have no singularities. So you don't talk about a hard part.
But I mean, this is now the complete matrix element, right?
This is the complete matrix element, right?
And in this case, it's only for Dralian-type processes, I think.
I mean, it's not Dralian type because we don't have the proton-proton in the initial state. So this is E plus C minus 2 jets. We are only looking at processes which have these singularities in the final state. We haven't talked about initial state at all. We'll see it next. So it's not really Dralian type. This is E plus C minus 2 hadrons where we have replaced hadrons with quarks and go on. So it's not really Dralian type. Dralian type will bring you more problems. There are more issues that you have to take or initial state singularities, right? All right, so far I gave you the phase space and I gave you the amplitude squared at NLO. So now let's combine them together to see what the R ratio from the real emission gives us. So this is R1 QQ bar G. Let me write it combining phase space. So now this is the R ratio, R1, real emission only, so QQ bar G. This is R0 times 2 times the strong coupling constant squared CF, 16 pi squared we're integrating over x1 and x2. This one goes from 0 to 1. This one goes from 1 minus x1 times to 1. And then we have times another factor, which I will write here, 1 minus x1, 1 minus x2, 1 minus x3, all of it to the power minus epsilon. And as an exercise, I will let you do this integral. You can ask Mathematica to do it for you, or you can use the beta functions to do it. It's a pretty simple one. Okay? I will give you the result. So you see now explicitly, once you do these x integrals, you see the double pole which is soft plus collinear you see a single pole, which is soft or collinear. And obviously, we cannot have a physical observable that depends on poles. So now, we need to add the virtual corrections. Okay, so the virtual corrections before I do that, probably I'll do something else. Before I go to the virtual corrections, I want, first of all, GS squared. In dimensional regularization, GS squared gets replaced by something else. So we are working in dimensional regularization. So the coupling constant GS squared becomes dimensionful because you introduce this mu to the power 2 epsilon. Okay, and just to remind you, alpha s for me is GS squared over 4 pi. And so now if I replace GS squared with what I have just written right now, R1 becomes now I have a dependence on mu squared in my result, so 4 pi mu squared to the power minus epsilon times 2 over epsilon squared plus 3 over epsilon plus 19 over 2 minus pi squared plus order epsilon. Okay, so now we are going to use the K-Allen theorem, the Kinoshita-Lee-Naumburg theorem, which says that singularities cancel in degenerate cases. So in this case, when the gluon becomes soft or collinear, the final state looks just like what you have for the virtual corrections, right? So it's clear that you have to include the virtual corrections before the singularities can cancel. And this K-Allen theorem is actually valid only for infrared safe observables. And the R ratio is actually infrared safe. So, following the K-Allen theorem, need to add the virtual corrections. And the virtual corrections, in this case, the only diagram that is going to contribute is 1, because in dimensional regularization, corrections to the external legs will give you scaleless integrals, and therefore they don't contribute. So, for the virtual corrections, we only have contributions from this diagram times the tree level. And here I will give you the result for the R ratio in terms of the virtual corrections directly. This is simple to do. It's much simpler than all these re-radiation calculations we've gone through. So I'll give you the result. Feel free to calculate this on your own. It's pretty simple, okay? So the R ratio from the virtual corrections in this case is virtual is R0 alpha S CF over 2 pi gamma 1 minus epsilon times S over 4 pi mu squared to the power minus epsilon times minus 2 over epsilon squared minus 3 over epsilon minus 8 plus pi squared plus order epsilon 2. And you can clearly see, once you add the re-radiation corrections to the virtual corrections contribution, the double pole cancels, single pole cancels, and then you have the finite piece. Okay? So clearly now the singularities cancel when you add these two pieces. So at the end of the day, the R ratio by itself simplifies or the R ratio becomes something simple. It's R0 times 1, that's my leading order, plus alpha S over pi, which is R0 plus R1 plus higher orders. So this is your R ratio at the N and O level. At the end of the day, it's just alpha S over pi times the 3-level R. Yeah?
What's the, in dimensional regularization, what is the origin of the 1/epsilon squared pole for the virtual corrections?
So virtual corrections also have, in principle, soft, so collinear and UV divergences. Here, there are no UV divergences in this particular case, okay? The way you can see it is the fact that at leading order, you don't have alpha S. So you cannot write a counter term for the virtual corrections. So there are no UV singularities from the virtual corrections. The other way you can see it is by writing down all the diagrams that you can have, namely this, plus the one where you have external leg corrections. You see something like this. And then distinguish clearly between introduce a regulator that separates your IR from UV singularities. And you will see explicitly that when you sum all these 3 diagrams, the UV singularities cancel. And then the IR ones will cancel between virtual and real corrections. Okay, so you have infrared singularities in the virtual corrections too. That's why you have these poles.
So this is a genuine...
This is infrared. Yeah, this is IR, right. But yeah, this is IR, pure IR. But I just wanted to emphasize the fact that in here we're not going to do some renormalization just because there is no UV singularity. So I apologize if I am taking you in a loop. But it's pure IR, yeah.
How do I know whether my quantity is infrared safe or not? Or whether I can use the theory?
Sorry?
How do I know whether my quantity is infrared safe or not?
So your quantity is infrared safe if it's not affected by the emission of a soft or a collinear radiation. If the observable does not get changed when you emit a soft or a collinear radiation, then it's infrared safe. For example, the multiplicity of gluons is not infrared safe. Why? So when you look at the multiplicity of gluons, 1, 2, 3 gluons, and so on, when you look at the radiation, the gluon can split into 2 soft gluons, and that gives you a soft singularity. This splitting does not happen at the virtual corrections side, and therefore the Kaelan theorem does not work here, and you will have a singularity in your final result. So this is not an infrared safe observable. So some observables are not infrared safe, other observables are. So your soft or collinear emission should not change the observable itself. It should be insensitive to it. Any more questions? This is what I wanted actually to show today. We are already past time, but if you have more questions, please go ahead. So you see all these algebraic steps, we had to go through them, and they feel boring, they look boring, but at the end of the day, they show you the physics. You can see explicitly where the singularities come from.